Greetings, detectives. Mrs. McKay here, and we are on our last clue for Case 4, Growth Pattern Change-Up. And what we're going to be doing now is we've had some experience with linear and exponential functions, and now it's time to know what is the best form to choose when you are looking for a linear or exponential function. When you're looking at a linear or exponential function, or you're needing to solve a problem, what's the best one to choose? Because there are different forms that we can use. We've learned a lot about different forms, especially with linear equations. So let's go ahead and fill in our learnings target that says I can choose the best form of a linear or exponential function when solving a problem. So hopefully this is going to be a short little lesson, and it will help you as you work on your team project efficiency experts. So what I want to do is I want to go ahead and review a little bit linear equations first of all. So here are some things that we've learned. These are some of the different forms that we've learned. Here's an example of an equation. Y equals 1/2 x plus 1. 1/2 x plus 1. Well, that is in slope-intercept form, and slope-intercept form has y equals mx plus b, where the m and the b are constants. So, in this situation, y equals 1/2 x plus 1. Which one is the slope, and which one is the y-intercept? You should be able now to very quickly and easily say that the slope is 1/2 and the y-intercept is 1. And the slope represents the rise over the run or the rate of change or equal differences over equal intervals, right? So those all mean the same thing, and that is right there. Okay? The next equation that we haven't really spent any time on, but I did introduce to you in class, is called the point-slope form. And the point-slope form, here's an example. If you saw this equation, y minus 3 equals 1/2 times x minus 4, you could say, oh, that must be the point-slope form. But really, you would use the point-slope form more when you were given a point. So the point-slope form says y minus y1 equals m times x minus x1, where y1 and x1 are the coordinates of a point. Okay? So if you're given a point and the slope, then you can write an equation using this form, the point-slope form. Y minus y1, that's a y1, equals m times x minus x1. So looking here at our equation, where is the slope? Where is the slope? Tell me, what's the slope? Yes, it's right here, isn't it? The 1/2. Again, the slope means the rise over the run, the rate of change, equal differences over equal intervals. And where is the point? Where is the point that is represented by x1 and y1? What is the point? Well, hopefully you saw that it is, looking for my colors, it's right here. -4, -3. So there and there. All right? So we've got slope-intercept form, we've got point-slope form, and we also have standard form. Standard form, x minus 2y equals negative 2. X minus 2y equals negative 2. And that's in the form of ax plus by equals c. Standard form is helpful when you're wanting to figure out the x-intercept or the y-intercept, because you can pretty easily just add 0 in place of the x to find the y-intercept, or 0 in place of the y to find the x-intercept. So finding the slope, or the rise over the run, or the rate of change in this one is a little bit trickier, because you really need to isolate that y and get the y by itself. But you could easily see that if I subtract x from both sides, I would have negative 2y equals negative x minus 2, divide by negative 2, and I get y equals positive 1/2 plus 2. Sorry, plus 1. So then again, my slope is 1 over 2. Okay? A little bit trickier to see, but you know that there's a 1 there. It's really the change in x and y, so you can see this, the coefficients of the 1 and the coefficients of the 2. It's just that you don't know whether it's a positive or negative, because you got to get them on opposite sides of the equal sign. Okay, so that's standard form. Sometimes standard form helps you when you're solving a word problem. It just kind of makes more sense to see it as a word problem. And you'll see some examples of that in the efficiency experts. Take a look at this next one. F of 0 equals 1. F of n equals f of n minus 1 plus 1/2. Well, this is a recursion formula. And a recursion formula, as you know, always talks about the previous term. So you always find out what the starting term is. F of 1 equals a1. So the first term in this situation, it told us what the 0 term was, and that's 1. Whatever the this little section right here, f of 1, f of 0, f of 2, f of 4, f of 10, it's always going to tell you where you start, okay, where you start. And then it's going to tell you what you do to find the next term. To find the next term, you always look at the previous term and you add the constant difference. So again, the constant difference right there. So over in this equation, where is the rate of change? Where is the slope? Where is the rise over run? Where are the equal differences over equal intervals? It's right here, isn't it? 1/2. That's our difference, our constant difference. So this is the previous term plus the constant difference. So you can see that each one of these equations is actually the same equation, the same function. Sorry, it's the same function, just in a different form. So we've learned 4 different forms of linear equations or linear functions. Now let's talk about exponential functions. We've learned 2 different forms of exponential functions. We have an equation that's an explicit form that looks like this. Y equals 10 times 3 to the x power. 3 to the x power. And really, that x needs to be right there in front of the 3. It's not 10 to the x power, it's just 3 to the x power. And our explicit form looks like this. Y equals a times b to the x power. B to the x power. Okay? Y equals a times b to the x power. And in this situation with exponential functions, if you remember, we have a change factor, or a constant ratio. And where do you think our change factor is, or our constant ratio, in this equation? You're right, it's right there. It's the 3, okay? The constant ratio. Or equal factors over equal differences. So our change factor is 3. That's the thing that we're going to be multiplying by each time. We're going to multiply our starting point, which is 10, our starting point, our f of 0, or f of 1, or wherever we're starting is going to be where we multiply by. And then we're going to multiply 10 by 3, and then we're going to multiply it by 3 again, we're going to multiply it by 3 again, and by 3 again. So 3 is to a power because we're multiplying 3 times 3 times 3, however many times our x is, okay? And then we have the recursive form, and the recursive form, I actually wrote this a little bit differently. So our recursive form, I want to show you a different way. It's actually written differently in my name, in my example, than it is over here. So let's make this a plus sign right there. Okay? So the first thing is we have f of 0 equals 10. And now we're going to say, if we want to find f of n, we'll just think about saying the next term. So f of n plus 1. The next term. The next term is f of n times 3. We could also write it like this. F of n equals f of n minus 1 times 3. But the way I've written it here is f of n plus 1, meaning the next term, is equal to f of n, which was the term before f of n plus 1, times 3. Both of these two mean the same thing. It's just really thinking about what they mean, okay? And the key here is, where is the change factor? Well, the change factor is right there, times 3, times 3, okay? So we've only really got 2 ways of looking at exponential functions at the moment, 2 equations or 2 forms, all right? And that's all we'll do in this case. So now let's take a minute and look at some examples. So, in his job selling vacuums, Joe makes $500 each month plus $20 for each vacuum he sells. Which equation best describes Joe's monthly income? Which equation describes Joe's monthly income? Is it 20x minus y equals 500, or is it y equals 20x plus 500? Which one best describes it? Which one best describes it? Well, it's this one, isn't it? Because y is the total amount, his income, and x is the number of vacuums, okay? And he makes $20 for each vacuum he sells, but he also makes just a base salary of $500. So he makes $500, so he always starts with $500, and then he makes $20 for each vacuum he sells. And when you add those two together, that gives him the income. This one, we could maybe make it work, but it's not really a good representation. Okay, so this is our better option right here. And this is in slope-intercept form. So sometimes a problem will be easiest to represent in slope-intercept form. Sometimes it's actually easier to represent in standard form, which is what this is. And let me just kind of quickly tell you an example. I bought 2 hamburgers or I'm sorry, I bought 2 hamburgers and 3 French fries, okay? And it cost me $5. 2 hamburgers plus 3 French fries equals $5. And so X would be the price of the French fries, X would be the price of the hamburgers, Y would be the price of the French fries. So in this situation, using standard form is better, okay? But neither one of these would work very well if I tried to write it in a recursive formula, would it? Let's look at the next one. Write the equation of a line with a slope of -2 through the point -2,5. Now, I have 2 different ways that I can do this. I could either try to graph it and look for the components to make it in slope-intercept form, or I might want to try using point-slope form. And that's what I'm going to recommend that you do. See if you can use point-slope form to write the equation of a line with a slope of -2 through the point -2,5. See if you can do that. What would the slope be? Or what would the equation be? So if I use point-slope form, I'm going to use y minus y1, which is the point, the y coordinate of the point, so y minus 5 equals m, which is -2, times x minus x1, which is -2. So x minus a -2 just becomes x plus 2. And now I've written the equation of a line. So I could use that equation, or I could simplify it, but I've just written the equation without having to substitute and try to find the y-intercept or anything like that. I can just quickly now say this becomes y minus 5 equals -2x minus 4, add 5, and I get y equals -2x plus 1. And there's the equation in slope-intercept form. Or if I wanted to put it in standard form, I could say, instead of adding the 5, I could add the 2x, add the 5 and add the 2x, and I would have 2x plus y equals 1. Okay? So either one of those, all 3 are equations. That's the equation, that's the point-slope form, that's the standard form, and that's the slope-intercept form. Okay? So when you're given a slope and a point, probably trying to use point-slope form is a great way to get it set up. You can also figure it out with a couple steps using slope-intercept form, but point-slope form works pretty quick and easy. And then you can put it in whatever form you want once you've got it in point-slope form. Let's look at the next one. Which form is best for graphing? Which form is best for graphing? Y equals 3/4 x plus 5, or f of 0 equals -2, f of n equals the previous term, f of n minus 1 minus 5. Which is best? Well, I think it's pretty obvious. This one's best, isn't it? Because we know how to graph this very quickly and easily. We can do 1, 2, 3, 4, 5 is our y-intercept, and we're going to go down 3 and back 4 because I don't want to keep going up. 1, 2, 3, 1, 2, 3, 4, and boom. We've graphed the line, okay? With a recursion, we would have to set up a table. It's going to take a little bit more time. We can still graph using it. We'd have to set up a table. We'd say x is when x is 0, y is -2. When x is 1, I'm going to subtract 5, so -7. And I'd have to do a lot of work to be able to graph that. Plot a few points. Well, not a lot, but at least plot 2 points, right? So slope-intercept form is a quick and easy way to use for graphing, all right? And then our last one is, which form is best for creating tables? Which form is best for creating tables? So think about, if I wanted to create a table for either one of these, how would I do it? Well, I'd have to plug something in for x and figure out what it is for y. Plug something in for x and figure out what it is for y and solve for y. So which one do you think would be the easiest way to do that? If I just picked some numbers for x and plugged in for y, which form would be better? Which would be the easiest? I think this one would be easier, mainly because your y is already isolated. If you picked this one, yeah, you could solve it, but you'd have to do a little bit more work, right? You'd say, put 0 in for x, you'd say 0 plus 2y equals 6, 2y equals 6, divide by 2, y equals 3, okay? In this one, you're not having to really solve for y. You don't have to isolate the variable y. It's already isolated. So you could say -1/2 times x is 0, 0 minus 4, y is -4. So you just save one step. So in this situation, this form is best, okay? But really, probably the best one, the best type of form for doing a table is using a recursion. It's using a recursion. Let's go back up here to this one. Look how quickly and easily it was to do this one, because immediately we know what our change factor is, and we can just add. So you can see that the different forms have different uses, and this will hopefully help you as you work on your Efficiency Experts report, which is quite long, and you really need to think about, and you're going to be creating a table that gives recommendations on which form works best for which type of problem. Now it's time to go ahead and write a key idea down at the bottom, and just something that's going to maybe help you. You might need to write 2 key ideas, or maybe it's just one key idea, like it's important to use the right equation for different problems, or it's important to know that each form still represents the same function, or that functions can be represented in different forms. Lots of different ways that you could write a key idea. The big idea is that you want to be able to look at it and know what this lesson is about. And that's all I have for choosing your function. So that was a nice short video, and I'll see you in class.